Hello, everyone, and welcome to today's webinar, Establishing EDS Quantification with Standards as a Technique for Everyday Use with FSQ in Apex. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we will follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Julia Maus joined EDAX as an application specialist in May 2022. Working out of the Munich, Germany office, Julia performs EDS and EBSD demonstrations, presents at conferences and workshops, and provides after-sales customer support. Her duties include on-site training courses, assistance with analytical problems, and scientific collaborations. Julia has been working with EDS and EBSD since she was an undergraduate student at Aalborg University in Germany. She received a Bachelor of Engineering specializing in surface technology and new materials from the university in 2018. During that time, Julia was hands-on with various microanalysis instruments, working with various metals and alloys. She completed her Master of Science in Geomaterials and Geochemistry in 2021. Her time as a graduate student gave her experience with minerals, ceramics, and glass materials. Now over to Julia.
All right, let me just change the slides. So thank you, Jonathan, for the introduction. As already mentioned, give me just a second, I have to remove this webinar thing. As already mentioned, today I'd like to talk about EDS quantification, especially with standards, as a method suitable for every day. All right, so approximately the next 40 minutes, we will deal with different quantification options. And to give you a small overview of this, I start with the basic principle of how to get from emitted X-rays to the composition of the sample. After that, I will dive into the quantification analysis of the detected signals. In detail, the normalized standardless quantification, the normalized quantification, and then the quantification with standards. Once we have gone through this, I briefly discuss further quantification possibilities resulting from these implemented options. And then I summarize everything at the end. Let's move to the first point, the introduction. So even though many of you are very familiar with EDS analysis, probably, I would like to give a brief introduction. We start with the SEM setup and its special geometry regarding samples and the detector systems. The electron beam then hits and interacts with the sample, causing different signals to emerge from the sample. The deflection of the electron beam causes a continuous X-ray spectrum, which is superimposed with the characteristic X-rays, which are schematically shown in this image here. These X-rays have an energy corresponding to the allowed electron transitions, which are therefore element-specific. For EDS, we are interested in exactly those X-ray signals and detect them with our silicon drift detector, convert them into a digital signal, and process them electronically in the pulse processor. After the signal has been detected and digitized, we can display the X-ray intensity in Apex in terms of counts versus energy in a histogram, and then the intensities of the X-rays can be used to determine the mass fraction of the respective element. Unfortunately, the composition does not correspond linearly to the measured intensity of the characteristic X-rays, and this is illustrated here using an example of iron silicide. The intermetallic phase has here about 66% weight iron and roughly 33% weight silicon, which correspond to a stoichiometry of 1 to 1, which is also reflected here in the atomic weight percent. So despite the significantly higher iron content, its measured intensity of the characteristic X-ray is significantly lower than the one of silicon. So in order to be able to determine the composition from those net counts, we need a model that describes all physical interactions. And what I would like to point out here is the role of the software. With current computation speed, we got so used to this. We certainly do forget what the software does in the background in order to deliver composition results. So here I highlight those values again. So let's dive into the model. By default in Apex, we work with eZAF, and in addition, we have a peak-to-background model implemented, which is called PeBaZAF. But I will not go into detail into PeBaZAF today. So let's have a look in the model to give you an overview of the relevant physical interactions. We take a brief look from the path from the generation of the X-rays to the actual digitization. So first of all, the beam energy must be high enough to ionize the respective element and to stimulate a transition. Then different probabilities have to be taken into account. First, we have a certain probability for ionization itself to occur. Then this excited state must be de-excited via the X-ray emission branch. And then we need to consider that each allowed transition has a different probability to occur. All these probabilities scale with the beam current and the beam time. Measurement time. When leaving the sample, these generated X-rays also interact with the sample itself, and the matrix correction, as it's called, has to be applied. This includes, for one, the atomic number, an absorption correction, and the fluorescence correction. How many of these X-rays which have left the sample are actually detected depend on the transmittance of the window and the detector solid angle, as well on the detector efficiency. Since most of those parameters depend on elements present or the landing energy, Apex works iteratively to determine the composition. So this is all implemented in Apex. So let's have a look at the software itself. If you haven't seen the software yet, this is what Apex looks like in dark mode. In the combined version for EDS and EBSD, and you can also see the review site on the top right. For each of the corresponding options, there's a matching header containing all relevant settings for the measurement. On the left, we have a project tree, which displays various samples and areas, and everything can be created on the left-hand side. All windows in the center correspond to the actual measurement. In this example, we see a SEM image of the sample, the associated spectrum of the point highlighted, and the quantification table. And for today's talk, we mainly deal with the quantification and its associated features, and they can almost exclusively be found here. So let's start with the default quantification, which is the normalized quantification. And now the important part of the webinar begins. Today we're dealing with quantification, which by its name already suggests that we're gonna dive into equation and formula, or at least they will play a role. But heads up, we will focus on the general understanding and only briefly use the formula. Don't worry. So as announced, here we see the eZAF model again from a different perspective. So in principle, all parameters that contribute to the model appear here as variables in the equation. Even though the formula does not look too complicated, if I can say that, we can already see quite a few variables. And that's the key word from this slide. It's a lot of parameters. And from this slide, I actually want you to take away that we have many parameters, and to be precise, we have too many parameters. So what does that mean? When we go into those equations in detail, we see that we have more unknowns than we have equations to determine the composition, and therefore we need to set another condition. And this condition actually describes that in the end, the mass fractions of all elements that we have must add up to 100%. That's basically it. That's called a normalization. And that is why it's called normalized quantification. And to see what that means, not in terms of formula, but in terms of quantification, we're gonna look at a short example. So here you can see a spectrum of a sample in which all the elements have been identified. And now we're gonna compare the quantification results from a quantification with standards to a quantification that is normalized. And what you can see that both results kind of resemble each other. So no problem here. We don't see an issue. Now let's look what happens if not all elements are identified. We remove vanadium, manganese, cobalt, and copper from the list. For the measurement with standards, we can directly see that the sum does not equal 100%. This already hints for missing elements. And due to the normalization, the remaining elements in the normalized quantification still scale to 100%, but the proportions have changed for each element. Even though in this case, the differences might appear relatively small, the misidentification of one, or in this case, 4 elements, cause additional error on all the other identified elements. So now I'm gonna take that to an extreme case. Additionally to all the elements removed previously, I remove iron from the list. And the quantification with standards already shows us 30% only. So here we have a strong hint that something is not okay. And this is actually a very effective way to turn an iron alloy into chromium nickel alloy with standardless normalized quantification. And you should always be aware that forgotten elements, artifacts, or surface contamination affect the quantification of all the elements, and that the results are not independent. And from the measurement itself, if you only have the standardless quantification results, you do not directly see that something is missing if you do not pay attention, of course, to your spectrum. If we look again at what this looks like in Apex, then the quantification window at the bottom left shows the normalized standardless quantification as default setting, as I said before. The reason that this is our default quantification is pretty simple. For this quantification, there is no further action of the user required, and the software can directly output the results. So you perform a measurement, you directly get results. You don't have to do anything. So this is very convenient and quick. As we just have discussed that the normalization condition can do quite some good, quite some bad. So let's see what we can do with non-normalized quantification to overcome the disadvantages if we misidentify elements. Coming back to my favorite slide, we saw here that we have too many parameters to actually solve the equation. But are there really too many parameters? So the normalization condition here that we've used previously has done its job, and we can safely ignore it. Now we have no choice to reduce, eliminate, or to determine some of the unknowns. And first of all, we can look at the beam current and the measurement time. For the time, it's a clear case. It's pretty simple to measure. Everybody can relate to that. The beam current can be measured with a Faraday cup, but here already it increases the effort required for the quantification. Regarding the detector solid angle, it's much more complicated to calculate it with a sufficient accuracy. So here we already struggle to be precise with those. And the decisive step we take here is that we're not interested in the value of the beam current or the time or the detector solid angle by itself, but we just put them all together. And that's the first step. We call it parameter G, probably. We can call it whatever we want. Here we always talk about the physical parameters of the setup. So in the following section, I always refer to them as the physical parameters or the reference. So now we call that G, okay? And then we look at the concentration. The more elements present in the sample, the more unknowns we have to determine. Therefore, we do a simple step. We just take one element. So we take a sample, for example, single element standard that has only one element and that has a concentration of 100%. Then we not only reduce the unknowns, but we suddenly also know our concentration. So now you might think that's strange. Why should I measure something from which I already know the concentration? But bear with me, I'm gonna get to that in a second. So our new approach changes. We do no longer want to measure the concentration in this step for the apex reference measurement, but we want to use an element, single element standard, which has a known concentration to actually determine the physical parameters of the setup. As I briefly mentioned, we call this process reference measurement. And this measurement allows us to determine some of the unknowns we had before and keep them and use them for our actual sample measurement. To summarize, we measure a single element sample, standard or whatever, to calculate the physical parameters that I just called G of this setup, and then measure our sample under, that's the important point here, exactly the same parameters. And then we can use the physical parameters determined from the reference or the value corresponding to that and perform a non-normalized quantification on our sample. The order here is not important, and the reference can be separated in time as long as we can guarantee that our parameters are identical. To show you what the workflow looks like in Apex, I can show you a video, and I have to stop it. It's faster than I can talk. So what I'm now gonna do is I'm gonna set up a new sample that I call reference. And I'm gonna measure on copper. Therefore, I activate on the software on the top, as you probably have seen. I'm doing that faster than I can talk. The reference symbol, and what I then do is, start the measurement. Let's go over it again faster. Then I say collect, and I need to tell the software which single element I'm using. So here I set copper. Then it will measure for some time, which is kind of adjustable. And once the measurement is finished, it will calculate a reference value assigned from this spectrum, and it's written here. And what I do now is I can save this permanently. I give it a name that is unique, and then I can either load here a reference or I can just type it in, and then I say save, and I create a new SSC, and this is now saved in at my system. So now I load a sample for which I want to perform non-normalized quantification, and I load the reference that actually corresponds with the same physical setup. And then when I apply the quantification, you can see that now the total is no longer normalized. It actually is non-normalized. And even though this looked like very long steps, I don't have to measure in the reference each time. I have to do that for the different setups I want to use once, and I can load them respectively. Okay, let's go into quantification with standards. So briefly to mention what quantification with standards usually looks like. That's what we call the K-ratio protocol. Here, to eliminate the physical parameters of the setups, a standard is measured under the same exact conditions as the unknown in a subsequent manner. And here, the concentration of the standard must be to some extent similar to the sample to avoid strong matrix effects. And then the characteristic peaks of that element are scaled relative to the known standard. I forgot to click, I'm sorry. And this is why EDS is called a comparative method. And in the first example, we have already seen some advantages of measurements with standards, and how now the question arises, why is this not the default quantification routine? But we clearly see that we have to take more effort in terms of time and knowledge, and this makes this method a rather unpopular one. So that's why we have implemented what we call full standards quant, or FSQ for short, in Apex, to offer quantification with standards in a rather quick and easy way. What do? We measure a reference, as I've described before, to determine the physical parameters of the setup. Then we measure our standard. Then we measure our reference again. And then we measure our unknown sample. And at first glance, I've increased the K-ratio protocol from 2 measurements to 4. So why should this make our lives easier? Rather than carrying out the subsequent measurements, Apex uses the reference measurement and impinges the physical parameters to the standard and to the unknown measurement. This allows to scale the differences between those measurements in terms of the solid angle and the beam dose, and the standard can then be saved and reused. So to illustrate that in a bit more detail, instead of performing sequential measurements, Apex uses the reference measurement to anchor those physical parameters in the standard and the unknown sample. So previously we have seen that we actually can remeasure like the reference every time, but we can also save it and store it in the software. So actually we do not have to do the reference each time. As a result, differences between those 2 measurements in solid angle and beam current can be scaled, and it's important that the standard and the unknown are measured under the same beam energy, but we are not so dependent that they are measured spatially and temporally in the close to each other. The most important point here is by separating these measuring systems, the standards can be stored, and I can apply quantification with standards in post-processing also on an offline system. The standards can be used for all the samples as long as the acceleration voltage is identical. If the standard and the unknown are measured on the same device, also the detector efficiency will be accounted for. So now I have to stop this video again. So I'm going to show you what that looks like in Apex. So first I'm going to create a standard, and then I'm going to apply a standard. And I will use the reference measurement that I had from before. So let's go. I go under Options, I say Standards, create a new standard. I give it a unique name, whatever I would like. Here I don't need to load it because it's already impinged from the measurement before. Then it's important to correct the target weight, and I save the standard and I say OK. And that's basically all I have to do to create a standard. And then I want to open my steel standard. What I do here, I will go into that in a bit. I have a list or a database of standards that I have previously saved, and I will just select all of them. And then I say OK. And then I say use standards and quantify. And now it will quantify me all the elements with the standard. And actually, when you would scroll to the right, you will see which standard it has used and which matrix corrections have been applied. And just to quickly tell you what I've done with when I selected use standards, we have actually 3 different modes for FSQ. Standard, multi-standard, and smart standard. Standard means that I can decide myself. I want to only use one standard, and I tell the software which standard. Multi-standard is basically that I can select multiple, and it will use a mean value. And smart standard is a very convenient tool because the software will decide itself which standard it uses. That's what I used in the video. And it's an algorithm that searches for a standard with the least matrix correction and apply it for the quantification. So when we have a look again at the little wizard that popped up when I said use standards, so the top of this view is basically a search function that I can use. I can either search in my database for standards using the periodic table. I can search by name. I can search also by composition ranges or by acceleration voltage. So there's multiple ways to filter out the desired standards. But as I've showed you, I tend to select all of them in smart standards and just let the software decide what it thinks is the best. And then I can quickly check in the applied standard for each element. So to summarize the benefits of the approach using full standards quant is that we have a fast routine, and if we stick with the same setups, we can load the reference and the standard, making the standard quantification a one measurement strategy only. So before I said, why should we make 4 out of it? If we actually have a reference saved, if we have a standard saved in the database, we only need to measure our unknown and activate the standards. So that actually reduces the workflow by a lot in time and complexity. So it also allows us to use a database and a software assistant guidance for selecting them. It still leaves open for a more advanced user to select the standards themselves in case they want to. And a huge benefit is that we can create databases of the standards. We can also share them theoretically with anybody else, and use them in post-processing remotely, which is very convenient when you realize, oh, this measurement, for some reason, I doubt it. I would rather go over it with standards. You can post-process it again. And experienced user, for example, can create standards and save them, create a database, and then the less experienced users could load them and do quantifications with them. So you also separate the actual process of saving a standard with using a standard. And as the model chooses the standard according to the matrix correction applied, and to some extent, the systematic error can be reduced. And if you have measured the standards on your system to create a database, you can also account for the detector efficiency. So I want to go into advanced quantification options also a little bit. We have seen the standardless customized coefficients previously when we did the standardless non-normalized quantification. Maybe you have noticed, maybe you haven't. When I applied the non-normalized quantification, I was using something was called SCC. So a little wizard popped open and I could select the different references. For all the elements appearing in this list, I have the option to determine standardless customized coefficients, or SCC. In the PeBaZAF model, they are called SF, just to let you know. They're basically the same, have a different name for the different models. And for each of those references we saved, we have the option to apply empirical corrections for all the elements. For certain elements, we can select them, put values manually. We can also use a measurement to do that. And that is, for example, helpful for high complexity applications where we want to account for changes in ionization cross-section. So I will give you a little example for that too. And again, we end up on our iron silicide sample to show you what that means. So the ionization cross-section with iron and silicon are shown on the right. And for some samples, it's very hard to select a proper beam energy because their lines that we are interested in are just far apart. And here in this example, for example, we want to reduce the beam energy. And as you can see with the red line, if we drop under a certain beam energy, our ionization cross-section just drops drastically. And when you have a look at the quantification table here with 10 and 8 kV, we see that our quantification just kind of drifts away from the target. And we see that the iron is overestimated and the silicon is underestimated. And that's from the changes in ionization cross-section. So if we still would like to perform a quantification, we have to account for the change in ionization cross-section for iron. And that is what we do. So we measure a single element reference. Here, for this example, I used silicon as a single element reference to account, as described before, for the solid angle and beam dose. And then I measure pure iron at the lower kV, so here at 10 and 8, to account for the change in ionization cross-section empirically. And I will save this correction value along with my reference measurement. And when I then want to quantify it, I just load the respective correction that I saved. And when I then perform standardless non-normalized quantification with the respective SECs, the iron composition and the silicon are stabilized to much lower kV. That's what you can see in the table in bold, or on the right-hand side in the diagram that the lines are now flattened out. So I give you now a little summary over what we have seen so far. We have seen the normalized quantification as a standard method for EDS, how it's done, and that it requires identification of all elements. I have introduced the reference measurement in APEX, which enables quick and easy non-normalized quantification, and also that we use the reference to store standards in a database so that we are able to reuse them at any time. Further, for full standards quant, we require reduced user input in terms of measuring and selecting the standards used for quantification. It also provides quick and easy access to quantification with standards and can therefore be used as an everyday routine. The most important insight I want to share today is that in terms of time and input, full standards quant can compete with the normalized quantification, whereas of course the quantification results are much better and trustable with standards. So that's now my point to thank you for your attention,